Alright, video lesson number 2. Like I said with the last one, if you want to try an example, just pause the video, try it out, see what you get, hit play, you'll see how I got the answer, and you can see if they match. Yesterday's lesson was on simplifying exponential relations or exponential expressions. Today we're going to look at how to solve an exponential equation. An exponential equation is any expression that has a variable as part of the exponent in at least one of the terms. So what that means is on one of the sides of the equal sign there is a letter in the exponent that we have to solve. So the examples we have are listed there. In order to solve these, we need to get the base the same. Essentially, if the bases are the same, then in order for one side to equal the other side, the exponents have to be the same as well. So the first one, we have 2 to the power of x equals 2 to the power of 3. What we can do is ignore the base. Like I said, in order for those two sides to be equal, because the bases are equal, the only way for the left side to equal the right side is if the exponents are the same as well. So what we know in that first equation is that x has to equal 3 for those two sides to be equal. In the next one, the base for each is 4. Again, we ignore the base and just write the exponents for it to be equal. Exponents have to be equal. So we have 2x equals 1, and we are going to solve for x. So we divide both sides by 2, and what we get is x is equal to 1/2. Same thing with the last one. Bases of both are 5. We need to make the exponents equal each other and then solve for x. I'm going to move that x to the left hand side. Gives me 3x minus x equals -7. 3x minus x is 2x. So we have 2x equals -7. Dividing both sides by 2, we have x equals -7 over 2. Now I noticed in the last video that the sound was a little bit off. I was kind of, we saw the writing, and then a couple seconds later we hear it. So I'm going to try with this one, writing it first and then explaining what I did afterwards. This part of the note is essentially explaining what I just said. In order to solve these exponential equations, we need to have both sides have to have the same base. If they have the same base, we can ignore that base, because the only way for these to be equal with the same base is if the exponents are equal as well. In order to do this, sometimes we have to change the base on one or both sides in order to make them the same on both sides. So what that means is, if we look at these examples, we have 2 to the power of x equals 4. Again, we need the base to be the same on each side. So what we're going to do is change that 4 into an exponential number where the base is a 2. To do that, we know that 4 is equal to 2 squared, so I'm going to change the 4 to a 2 squared. Now that the bases are the same, we can ignore them and just make the exponents equal each other. So what we found out is x equals 2. Same thing with the next one. In this case, we know 27 is 3 cubed. 3 times 3 is 9, times another 3 is 27. When the bases are the same, we can ignore them, just make the exponents equal each other. And once we've made the exponents equal each other, we can solve for x. So the answer to this one, we have x equals 3 over 2. Now, sometimes you have to change both sides. 4 to the power of x equals 8. We can't change 8 into an exponential number with base 4. There is no even nice exponent where 4 to that exponent equals 8. So what we have to do in this case is change both sides. Both 4 and 8 can be written as an exponential number in base 2. So that's what I'm going to do. Change the 4 to a 2 squared. Change the 8 to a 2 cubed. On the left-hand side, we have a power to a power. We have 2 squared to the power of x. What we need to do is multiply those powers together. So doing that gives us 2 to the power of 2x on the left-hand side. On the right-hand side, we have 2 to the power of 3. Again, we're ignoring the bases and just writing the exponents equal to each other. And once we do that, we are solving for x. Last one like this, we have 5 to the power of 3x minus 1 equals 25 to the power of x plus 4. Again, to figure out what that common base has to be, we look at the numbers. I would always look at the bigger number and see, is there a way I can make the base of that bigger number whatever the base of the smaller number is on the other side. So I'm going to look at this and ask myself, is there any way to change that 25 into a number that is base 5? We know that we can change 25 to 5 squared. Once we've done that, we have, again, a power to a power. Now, the difference here is that power, the exponent outside the bracket, it's 2 terms. It's x plus 4. So you don't have to do this step, but it would help. It will help. We're multiplying that exponent in the bracket, the 2, by the entire exponent outside the bracket. So what I'm going to do is put that exponent outside the bracket in brackets itself to show that it's that 2 times the whole thing. And from there, I'm going to do distributive property. So we have 2 to the times x, which is 2x, plus 2 times 4, which is 8. From here, we're just, the bases are the same, so we're ignoring them. We just write the exponents equal to each other, and we need to solve for x. So we have 3x, we bring that 2x over, so it becomes negative 2x. We have 8, and we bring that negative 1 over, so it becomes plus 1. 3x minus 2x, it's 1x. 8 plus 1 is 9, so we get our answer to be x equals 9. Again, looking at the first example there, we're doing the same thing. We want to solve each of the following equations using equivalent bases. I would ask myself, is there a way to turn that bigger number, the 125, into a exponential number with the base of the smaller number 25? 25 times 25 doesn't give us anything. There is no, it doesn't give us 125. There is no nice exponent where we can have 25 to that exponent equal to 125. What that means is we need to look smaller. We need to change both of the bases. Now, we know that 25 is 5 squared. So we should look at, is there a way where we can have 5 as our base, and what exponent will give us 125? The answer to that, so 5 squared is 25. 25 times 5 is 125. So what that tells us is that 125 is equal to 5 cubed. Once we're here, we have on both sides a power to a power. So we're going to multiply those together, the exponents on both sides. Once we've done that, we're going to do distributive property on those exponents. Now we have our bases the same. We've done distributive property on the exponents. So what we're going to do is ignore the bases and just make the exponents equal each other. Once we've done this, we need to solve for x, so we're going to move all of the x's to one side and the numbers to the other. So again, 3x, positive 3x, moving it over becomes negative 3x. That negative 2, moving it over, becomes plus 2. 4x minus 3x gives us 1x. 12 plus 2 gives us 14. The next one isn't so much a common base. We just need to know that we're looking for 4 to what power gives us 1. We need to know that, again, anything to the power of 0 is 1. So this would be 4 to the exponent 0 equal to 1, or x equals 0. Now, this next one here on the left has a fraction as a base. Usually when you have a fraction as a base, like 1 over 2, what we should do, if there is no exponent on the 2, is the same as there being a 1. And we can flip that base by making the exponent negative. It's a positive 1 on the 2 on the bottom. So if we bring the 2 to the top, that exponent becomes negative or negative 1. So what we have on the right hand side is an exponent in base 2, an exponential number in base 2. What we can do on the left hand side is turn that 8 into an exponential number in base 2 as well. 8 is equal to 2 to the power of 3. We don't need that bracket. What we're going to do is multiply those two exponents together. On the right hand side we have a power to a power, 2 to the negative 1 to the power of 1.5x. So doing that gives us 2 to the negative 1.5x. Now that we have that common base of 2 and our exponents are completely expanded, we're going to ignore the base we're going to write the exponents equal to each other, and we're going to solve for x. So we have 3 divided by negative 1.5, which is negative 2, equal to x. Those negative 1.5s on the right hand side cancel each other out. Couple more examples. Again, at any point you can pause the video, try them out, and see how you're doing with it. If you feel like you have a good grasp on the concepts, now they are much harder examples, so it doesn't hurt to try them, but you can always skip a little bit ahead in the video as well. So same idea. This 27 we know is 3 cubed. I'm using 3 as my base because on the other side we already have 3 as a base. Here we have 3 to the power of x to the power of x plus 5. We're going to expand those exponents. So we have 3 to the power of 3 times 16 minus x equals 3 to the power of x times x plus 5. Again, we're going to distributive property. We have the bases the same, so we're going to ignore them and write the exponents. Now, this one's a lot trickier because when we expand those exponents, what we end up with is a quadratic number, or a quadratic equation. In order to solve a quadratic equation, we need one side to be 0. So what we're going to do is move all of the numbers to the right hand side to make that left hand side 0. The negative 3x becomes a positive 3x. The positive 48 becomes a negative 48. From here we are looking, there's two ways we can solve this. We can either factor it, or we can If we can't factor it, we can use the quadratic formula. Now, to factor it, it's a simple trinomial, so we're looking for two numbers that multiply to negative 48 and that add to positive 8. Negative 12 and positive 4 would give us negative 8, which isn't what we're looking for, so we would need 12 and negative 4 to give us positive 8. We have 0 equals x plus 12, x minus 4. And what that means is we have two answers that will make this work. We can either have x equals negative 12, or we can have x equals 4. Alright, so looking at the next example on the left there, this one is a little bit more complicated because we have that exponential, the 2 to the x plus 3, but we also have a number times that, which is the 7, and a number at the end, which is added, which is the 3. Now, in order to solve these kind of questions where we're trying to find that common base, we need it to be just either a number and an exponential on one side and a number or an exponential on the other side. We can't have these numbers, these exponential numbers times a number, and we can't have anything added on to the exponential number at the end like that 3 is. So what we are going to do here is we are going to solve for that exponential number, that 2 to the x plus 3, by moving everything else over. So we're going to start by moving that positive 3 to the other side and subtracting 3. That should be a 4 on the end there. And then what we're going to do from there is divide that 3584 divided by 7. And what we get is 2 to the x plus 3 equals 512. Again, once we've done that, so we have this just an exponential number on one side and just a number on the other side, which is what we need it to be in order to use the common base like we've been doing. Now, 512, you may need to play around with it in your calculator a little bit, but that you would find that 512 is equal to 2 to the 9. So we have that common base of 9, and I knew that the base had to be 2 because the base on the left hand side is 2, and there isn't really anything that we can reduce that to 2. So once we have that common base of 2, we ignore the base, just have the exponents equal each other, and once we've done that, we solve for x, and we end up with x equals 6. So now we're going to look at the one on the right. Same idea. Again, we have that base of 2, so that exponential number with base 2, but we have something multiplied by it, which is the 1 over 8, and we have something subtracted this time, which is the negative 3. So like before, I'm going to get that exponential number, the 2 to the 2x plus 1, by itself. By moving everything else over, that negative 3 becomes a positive 3. 1 plus 3 is 4. Now what I did was I made that 1 over 8, I kind of separated it a little bit with that dot, that multiplication sign, just to show how I got that. I kind of multiplied a fraction by a fraction. We do the top times top. So 1 times 2 to the x plus 1 gives us this on top, that 2 to the power of 2x plus 1. On the bottom we have 8 times 1, which gives us the 8 on the bottom. From here, I'm going to do a half cross multiply to bring that 8 up to the other side. what that gives us is 4 times 8 on the other side, or 32. And 32 is equal to 2 to the power of 5. So I'm going to change that 32 to 2 to the power of 5. Gives me a common base. So I can ignore the bases, just have the exponents equal each other, and eventually solving for x, we end up with x equals 2. So just to recap, in order to solve these exponential equations, if we can make the base on each side the same, I would say that is the best route to go. In order to do that, change of base, we need it to be just kind of an exponential on one side, so an exponential number, and the other side has to be only either an exponential number or just a number. Essentially, we can only have one term on both sides, so if we have anything else multiplied or added or subtracted, we need to get rid of those so that we only end up with that exponential number on the one side. Now, sometimes you won't be able to find equivalent bases. What that means is we can't do this kind of equivalent base, ignore the base, make the exponents equal each other. What we have to do instead, there's a couple ways we can do it. The first way is we're going to approximate the value of x in each equation, and this essentially amounts to guess and check. So the first one, we have 2 to the x equals 20. Now, by doing this, we know that 2 to the power of 4 is 16, and 2 to the power of 5 is 32. So what that's going to tell us is that our x should be between 4 and 5. It's a little bit closer. 20 is closer to 16 than it is 32. So I'm guessing my x is going to be a little bit closer to 4 than it is to 5. So what I'm going to do is start off, say, try x equals 4.2. 2 to the 4.2, I'm going to find out what that is equal to. Gives me 18.4. Close, but not quite. Again, so I'm just going to try another number, say 4.4. Gives me 21.1. Closer, too big now, so let's try, say, 4.35. Gives me 20.4. Again, we're getting closer, but we're not quite there. So we have 2 to the power of, say, 4.31. Gives me 19.8. 2 to the power of 4.32 gives me essentially 19.97, or I would call that 20. So using guess and check, what I found is that my x is approximately equal to 4.32. Now, we could keep going, but you can kind of see that it's a long process to do this guess and check, which is fine. Again, it might take up some time on a test, so I'm going to show you a different way. So I'm just actually going to ignore those next two and move right on to solving exponential equations using logarithms. Now, we only do this when we can't find that that common base, that equivalent base for our exponential numbers on either side. What a logarithm does, it's a button on your calculator. It would most of the log buttons just say log, L-O-G, and essentially what happens is when we take the log of both sides of an equation, what we can do is bring the exponent down in front of that log. So you'll see here that what we have is log of x to the n, and that exponent n actually comes down in front of the log. So log of x to the n is equal to n log of x. So essentially we've brought that exponent down, and we'll see how that becomes handy. we have 3 to the power of x equals 5. What I'm going to do is take the log of both sides. So I have log of 3 to the power of x equals log of 5. Now we have to do it to both sides because whatever you do to one side, you also have to do to the other side as well. What happens is I can bring that exponent down front, and so what I end up with is x log of 3 equals log of 5. Now log of 3 is just a normal number. If you put it in your calculator, you end up with a number, and what that means is we can work with it the same way we would work with any numbers. When we have on the left hand side here, we have that x and the log 3 beside each other. What that means is that they are multiplied. So if we want to get x by itself, what we're going to do is divide both sides by log 3. So what we end up with is x is equal to log 5 divided by log 3, or x is equal to 1.46. If you want to check, you don't have to, but we can do 3 to the power of 1.46 in our calculator, and we end up with 4.97, or essentially we end up with 5, which is what we're looking for. So we'll try some more examples. Again, 2 and 12. 12 we can't turn into a number that is base 2, so we can't do that equivalent base. We need to use logs instead. So we're going to take the log of both sides, and I'm going to put brackets around that exponent and bring it down front. Again, when you take the log of both sides, whatever the exponent is, it doesn't have to be just a single variable, just an x. If it's an equation like x plus 1, we can still bring the entire thing down in front of that log. So that x plus 1, again, I'm going to put in brackets to show it's the whole thing multiplied by log 2. We want to get that x plus 1 on its own, so we're going to divide both sides by log 2, and what we end up with is x plus 1 equals log of 12 over log 2. Log 12 over log 2 is 3.58. We have x equals 3.58. That positive 1 becomes a negative 1, or x equals 2.58 is our answer. So again, to recap, we took the log of both sides. Doing that, let us bring that entire exponent down. We isolated, got that what was the exponent by itself, and then we solved for x. Now, just like when we're doing this with a common base, what we did before, in order to use these logs, we need it to be just a single exponential on one side and a number on the other side. So, for example, we have 4 times 2 to the power of x minus 3 minus 4 equals 34. Again, in order to do this, we need to get that 2 to the exponent x minus 3 by itself. So essentially we are going to solve for that exponent. That negative 4 becomes a positive 4. We have 34 plus 4, which is 38. We're going to divide both sides by 4, and that gives us 9.5. And now that we have the left-hand side as just an exponential number and the right-hand side as just a number, now what we can do is take that log of both sides. And again, when I do that, I'm going to put the exponent in a bracket. I'm taking the log of both sides, and that exponent we can bring down in front of the log. Once I've brought that exponent down, I'm going to solve for it by dividing both sides by log 2. We get x minus 3 equals log of 9.5 divided by log 2, or 3.25. Finally, that minus 3 becomes a positive 3, giving us, on the other side, giving us x equals 6.25. So again, just to recap, when we can't get equations to have a common base, we're going to use logs. The log, when we take the log of both sides, it allows us to bring the exponent down. In order to do that, we need to be just an exponential number on one side and just a number on the other side. So like this last question, we may have to solve for some variables in order to get that to work. So, like I said in the last one, if you got a different answer than me, just comment and I will check it over and let you know if you were right, or let you know maybe where you may have made a mistake to get that answer. The homework for this one is the worksheets. They will be posted as well. If you're in class on Friday, you can get them from whoever is in for me. Let me know if you have any questions, and I think I will be putting another video lesson up on Sunday for Monday's note. Essentially, Monday will be a work period with me in the classroom to kind of answer any questions that you might have regarding the lessons that I was not there for, that you should have gotten by watching the videos. Thanks. Have a good weekend and see you on Monday.